We have Joe Price from Brigham Young University. Joe and I we overlapped in graduate school. No one ever got us confused because this is the smart Joe, without question. So he's, as you all know, works in the economics of the family, has published in top journals in the field, the Quarterly Journal of Economics, the Journal of Labor Economics, and top interdisciplinary journals, demography. And today we're fortunate to have him here to talk about a large project that he's working on at BYU on linking historical records to study health and longevity. Joe, thanks so much for being here.
Thanks. Okay, so let me make my pitch just to start. So I am working with Steve Ruggles on some of this stuff. And so if you love using IPUMs, then the data that I'm going to be talking about today will eventually be kind of become part of the IPUMs universe, which will be easy for you to use. The only thing is you have to care about stuff that happened before 1950. But let me make a case for why this is kind of broader than you might have originally envisioned. So what I'm going to talk to you today is about how we might be able to link together historical records to study health and longevity. So just to give you a little bit of background, Scandinavian countries have fantastic data. They have these registers that allow you to link together people's birth and marriage and death records, their labor and health records, and you link it all together because they have nice little identifiers. The only downside is that a country like Denmark doesn't have a ton of within-country variation. Same with Sweden and Norway. The US has a very decentralized policy-making environment. We have 50 different states, we have 3,000 counties, we have all these cities, so you have this nice variation that happens. And so let me just give you some idea of what's possible here. This is just from Joe's CV. Sorry to pick on Joe. But you have child access prevention laws, minimum wage laws, medical marijuana laws, Good Samaritan laws, cigarette taxes, anti-bullying laws, state physical education requirements, parental involvement laws, and these are on Joe's CV just since 2016. So what this gives you is just an idea of the variety of policies that we get to explore in the United States because we have this decentralized policy-making environment where states are doing different things all the time. Some laws get passed much earlier than others, and so we can exploit this to understand the effect of some of these policies on people's lives. Now the nice thing about the data I'm going to show you today is you can look at very long-run outcomes. For example, when our outcome is health, it can be helpful to have measures that capture long-run measures of health. For example, I've studied eating vegetables in kids, and everyone's always asking me, well, what outcome measure are you going to look at? I'm like, I don't know. Like, you eating your vegetables, it doesn't help you until like way down the road. In fact, if I wanted to measure the effect of veggies in the short run, I'd have to get at the cellular level and look at kind of like things going on in the cells. If I wanted to measure it as an economist, I can't measure it until much, much later in life. So the nice thing is we can then look at policies that might affect you long run. It might even affect you intergenerationally, in that things that happen to you as a child might actually affect your children's outcomes. And then we're really focusing on lifespan in a lot of these projects. And the thing I like about lifespan is it's comparable across place and time. In that if I want to think about this policy increases lifespan by 2 years, I could potentially compare that policy across different countries, across different time periods. Whereas almost any other measure we think about, like income or test scores, you have this kind of complicated problem of like, how do I compare extra $1,000 of income in one time period versus another? And so lifespan has this really nice units feature. So this is our goal. Starting in 1850, the United States would list every household member in the census. And then now we have the 1940 census available. So what we want to do is take each person that was available in each of the census years between 1850 and 1940 and link them across every census record that they appeared. So what you're going to have is a longitudinal data set that has 217 million rows. And then it has identifiers for each of the censuses that person shows up in. And then using those identifiers, you can merge in whatever is available in each of those census years. So some census years has measures of wealth, most have measures of occupation, most have measures of marital status or some kind of family structure variables. And then starting in 1940, you get all the good economic stuff like education, wages, income. The other thing you can do, so the one data set basically links census records for a person. Another data set gives you relationships between each of the people within the 217 million. So I could tell you this is your ID, I could tell you who are your parents, who are your siblings, who are your children, who are your spouses. I can tell you who your first cousins are, who your second cousins are. And so you can start to understand someone's kin network. Now the kin network can be really important for many reasons, but here's just one example. Imagine I wanted to classify you as poor or disadvantaged. You know, one way we might do that in modern data is just say, do you have a single parent? Okay, so we use single parenthood as like a proxy for disadvantage. Well, it turns out, like if you read a book like Hillbilly Elegy, you realize that, you know, even though you might have a single parent, you might have other family members that have more stability in their life. And so I might have one kid who has a single mom, but has 5 uncles that are all college educated and have good jobs. And so we might not want to think of that as the same disadvantage as if you have a single mom and all of her brothers are incarcerated or, you know, having tough things going on in life. And so I think we're going to have much better measures of what it means to be from, you know, a disadvantaged family or an advantaged family. Yeah.
Can I ask the obvious question of why stop in 1940?
Well, because there's this rule in the U.S. There's a 72-year rule. So you're right. So if I were to do this in an RDC, then I wouldn't stop at 1940. I'm kind of an open source guy. I like to be able to share my data and code with other people, and so I kind of envision this is going to be a data set that will be used by scholars outside of an RDC environment.
I mean, could you in principle take this into an RDC?
Yeah, you could in principle take this into an RDC environment and then link it in. So basically, as long as you, so one thing you could imagine is if you assigned picks to all these and those picks were the same as the Census Bureau's picks, then you could just bring this data set into the Census Bureau and link it all the way up to the modern data. So, I mean, the nice thing there is, you know, they're picking other data sets like the HRS and the PSID, and so this could potentially give you lots of background things to control for in a PSID environment. Okay, now these are the numbers involved. This is the US population in each of the years. And then what we do is in each of the years we say, well, how many of those people weren't in the previous census based on their birth year and their immigration year? So you can see in 1850 everyone's new, not that they're new to the United States, it just means they're new to our data. And then in 1860 we add another 10.9 million people and then 12.9 million people. And so this is the number of person year records, so 673 million. And then this is the number of unique people in the data set, about 217 million. Now these two numbers become really important because then you can start to think about, well, how many records per person will I have? About 3. And then I'll show you later, you can actually use these two numbers to figure out how many matches should exist. And so you can then start to think about what your match rate looks like. Okay. So any questions before I jump into some other stuff? Yeah.
So for those people who are not in the later census, are they out because they died or because they just not died?
Oh yeah, that's a great question. So you can actually then, basically you know you had 23 million people, and then you added this many people, but this is how many you have. So if you take this number plus this number, and then subtract this number, that's how many people either left or died. So those are actually unlinkable people. So it's helpful to know that number because if you think that this is like, if you're trying to match everyone, it's just literally impossible. But if you add, by having all these numbers, you can actually figure out what the unlinkable set will be. But you're right, mostly it's people die.
Can you describe the people who leave that don't die?
The people that leave that don't die. That's harder to know. So
I guess I don't know what the mechanisms are through which you can leave the census record.
oh no. What I mean by leave, you leave the country.
Oh, okay.
Oh yeah, and then the other problem is there is under enumeration, so you might sometimes we just miss people.
Right. Okay.
We're trying to get that number. It looks like it might be 7%, but we're not totally sure on that.
Oh,
Okay. Now the nice thing is, so what we tend to do is we tend to link back. So if I know, so of these 31 million people, I know how many of them were born before 1850, and I know how many of them immigrated before 1850, and so I only try to link those that are linkable. When you link forward, the hard thing is you don't know if they're linkable, because they could have died. And then the other thing is we find death dates, and that helps us take people out of the sample and not try to link them. Now let me just be clear, this is the census record part of it. The other nice thing about doing it up to 1940 is this is all public data. You can see the names of people, their birthplaces, their birth dates, and so then this becomes potentially linkable to any other data set. So you have military records, you have death records, you have marriage records, you have school records, you have patent applications. So you have this like wealth of data that you can tap into. And what I'm going to show you also here in just a little bit is what you could potentially turn into usable data is almost unlimited. And so there's some pretty cool advances. that are happening with regards to OCR and handwriting recognition that makes it, as long as it's on paper somewhere, anywhere, you could potentially turn it into a usable data set. Okay, so here are some of the benefits of fully linked data. You can study long-run and intergenerational effects of various shocks in public policies. You can track migration, mobility, and the boundaries of markets. You can exploit information about the kin network. You can assign treatment exposure based on birth city and where you live over time. You can combine covariates from multiple data sources. And since it's using historical data, the final product can be shared with other scholars and additional data can be merged into it. I don't know, are you sold? Is this cool? Is this possible? Okay. So let me tell you what we're doing in this regards, because actually this kind of hope to link together lots of records is being carried out at lots of different great universities around the country. And machine learning has become the powerful tool to make it possible. And what I'm going to try to pitch today is that there's a low-tech complementary skill that we want to employ, and this is called genealogy or family history. Okay. So what I'm going to try to pitch is that we can combine what I would call the kind of traditional approach to linking records with the modern approach to linking records. And I think if we only do the traditional approach, it's going to take forever. And if we only use machine learning, we're going to do a really bad job at it. But if we combine the two, we could potentially get this done really, really fast. And when I say really, really fast, I literally mean by December this year. Okay. But here's the two ways that family history can contribute to this. So people do careful family history research and identify multiple records for the same individual. So I think I was talking to Roger, he says his wife does this kind of stuff. So, people like Roger's wife, they go and they look for records and they attach them to a person. And you might see a person's profile and it might have 15 records attached to that person. Every pairwise combination of those records becomes a training set. And what the machine starts to learn from those training sets is the way that names can be misspelled. It starts to learn that birthdays are sometimes off a little bit, or that when someone was born in Ohio, they might say later they were born in Illinois, but they're unlikely to say Ireland. And so the machine starts to learn which patterns are possible. So this is just saying, let's just look at everything humans have ever done with family history and use it to teach machines how to do the same thing. And then the other is that traditional family history tools can help us with groups that they're just really hard to match. So this includes women, immigrants, people who migrate a lot, or who have names that get misspelled. So I can't remember who was talking about borders. Were we talking about borders? So borders are like super hard to link from a machine learning perspective. But, so you might not ever be able to learn anything about borders. But genealogists have developed tools to track even borders. Women are also tricky. They changed their last name. During World War I, a bunch of Germans stopped being German. They changed their last names, and they said, I'm not born in Germany, I was born in Poland. And so these all become complicating things that you might want to use some traditional tools to get at. Okay, so here's the outline of the talk. I'm just going to describe what my lab does. I'm going to describe a new approach to record linking, and then I'm just going to show you a couple results related to health using this new data. But what I've discovered is every time I present this stuff we're working on, I pick up a co-author or two. Okay, so yeah, I love working with people. So if something that you're interested in intersects with this, and up until a few years ago, I never did economic history. You only use modern data. But what I've discovered is that almost every modern data question has a historical analog that we can tap into. So it's really hard to actually find a policy debate today that doesn't have something similar that we've done in the past. So I think Catalina was just telling her, or we both had heard about the same story, but in the 1930s, California and other places just rounded up Mexicans, put them on trucks, and just sent them back to Mexico. Okay, and so we could actually potentially go back and look at those people. We could look at communities where they were pulled from, and we could maybe learn a lot about what happens when you just forcibly eject people from a country. Okay, so this is my lab. I have 45 research assistants. So if you want to learn more about us, we're rll.byu.edu, but it's a combination of students who can do hand linking using traditional tools, and then a bunch of students who are really good at machine learning. And so right now I have about 12 students doing pretty high level machine learning using Python and other tools. Okay, so these are the two things we do. We extract data from historical records. So we do something called line segmentation. And all line segmentation is I've got a document and I need to know where the stuff is. And I just tell the machine, this is where the lines are, and in between the lines is information that's useful. Once you've done line segmentation, then you can do OCR or handwriting recognition. And then you might want to do some natural language processing afterwards to turn the data into usable stuff. So that's the first thing we do is we pull data from historical records. And I'll show you some examples. And then what we do is we link those records together. So here's an example of a record that you might want to pull stuff from. So it turns out that Family Search and Ancestry had people go and hand type all the genealogy stuff. So here's Joseph Price. So they put that, male, race, marital status, and some other things. Well, it turns out that right here it tells you how this person died. And that's actually a really important variable for health economics and other things. It helps us understand the rise of cancer. It helps us think about public health interventions that might have affected different types of death. So Ohio has 2.8 million of these records, and nobody has this field right here. So the question is, could you potentially teach a machine how to read that stuff? Now, the nice thing about this is a pre-printed form. And so you do something called form registration, which is you have the machine figure out where the pre-printed parts are. So notice that there's this really nice phrase called cause of death, and it's typed. So actually once the machine finds that, it can orient itself on the sheet. And you can basically say, I want this stuff right here. You have to do some de-skewing to the image to get it to straighten out. But then once you've boxed this in, then that just becomes a handwriting recognition problem. And at that point, right now we have a whole bunch of humans typing out like 20 or 30,000 of these. And then we use those to train the machine, and then you let it loose on the other 2.8 million for Ohio, and then you just let it loose on every other death certificate for the entire country. And then the nice thing is you have a lexicon, we actually have a list of every possible cause of death. And then once the handwriting recognition does its job, it matches it up with the lexicon and does some kind of post-processing to clean it up. Though I did see one yesterday that was strangled while in a fit of anxiety. It was on a military base. It was strangled while in a fit of insanity. So this was probably some PTSD problem. But we did not have that in our lexicon. We did have strangled, so strangled picked it up, but not the in a fit of insanity. So the machine would be like, okay, I don't know why this phrase is here. I've never seen it before. So you're not going to have like a perfect classification, but you can get like broad classes of causes of death. Yeah.
How do you determine how large a training set should be?
A little bit trial and error. So you get your training set, you kind of split it in half, you train on half of it, you test on the other half and see how well you do. And then there's like rules of thumb because we've done other projects before and you get an idea of like how much the training set has to be. Okay. The other thing we can do is since we already have an index of some of these other fields, we could actually do the machine learning on some of these other fields and get an idea of how much training data it would take to get a word like that. Yeah.
With their classification algorithms, are they probabilistic? Like, do you get any kind of sense of like errors in variables if you're using these as?
Yeah. So you could potentially create a match score for how sure you are of that thing. And then what will often happen is you'll create a cutoff for that match score. And so if you're above it, then you'll know that you have it. And then you might have a human check those that are in the fuzzy zone. And then those in the fuzzy zone can become future training data.
But have you thought about using sort of the classification sort of variance?
Yeah, I know. I haven't. I know there's some statisticians that really like doing that kind of stuff, especially on the match scores for almost any record. So what they would do is they'd say, because one of the groups we worked with, they said, I don't need an exact match. I just want to have like the 5 possible matches and then some match score across them, and then we will do some kind of multiple inference approach. So I haven't gone there. I actually really want to know the truth, but I could probably tell you what the second best thing would be.
I guess more I'm thinking like,
Yeah.
your idea is this is only the first step, right?
Sure.
And then you're going to use all this data in sort of standard.
Exactly. Yeah.
studies, right? So I mean, you might want to acknowledge
That there's some
there's
measurement
some measurement error if you're using these, say.
Yeah, that's a good point. Yeah. So I haven't thought very carefully about the second stage use.
So when you're cutting the data to get your training example, on what dimension you're cutting the data?
There's two training. One is you train the model how to figure out where this little thing is,
Right.
and that doesn't actually need a lot of training data because actually the forms are pretty easy to get to do what you need them to do.
Okay.
But then actually being able to read that phrase, that's where you have we actually have humans go and read that phrase, and then we have multiple people read them, and then we compare to make sure they got the right thing. And we actually have them recorded in 2 different ways. They literally write character by character the best that they can guess, and if they can't tell what a character is, they'll put in question marks or asterisks. And then what we do is at the end, we also have them write down what they think is the correct classification for that thing. So you can think about actually two ways to do the handwriting recognition. One is like character by character. The other is just, I don't really care about character by character, I just want to know what that thing is. And so you can kind of see this like word vascular disease right here. So I might not know exactly, once you know that this is vascular disease, you kind of know that this is probably cardio. So even if I can't get the characters, I could just tell the machine, yeah, this is cardio-renal vascular disease. And so I might be able to guess it, even if I can't read the letters. Because the doctors, or the coroners, to be honest, they sometimes go like, and so you kind of know what they're saying, but the characters don't make any sense.
Is it a random sample that you're training on?
Yeah. Okay, here's another example. This is the AMA, the American Medical Directory. It lists every single doctor in the entire country. Now, if you just run OCR on this, it does a really awful job because the lines get blurred together. I mean, I blew this up quite a bit. The text is crazy small, and the distance between the lines is really small. So OCR has a trouble with this. But it turns out that you can actually use the line segmentation tools to figure out where the lines are. And then you grab that little image, you pull that image out, and then you run the OCR on just that little image. So basically, if you separate the line segmentation from the OCR problem, then you can solve the OCR problem. Okay. Or the other thing we can do, this was some people that participated in the Civilian Conservation Corps. And we were just given a flat file that said, these are people, can you tell us more about them? So we were able to link them to their census record, their death record, and we were able to even find their social security numbers. And so once you have their social security numbers, then you can go and potentially get all their earnings history. So this flat file that we were given, we weren't told which ones were accepted or rejected, but there were people in this flat file that had been accepted for the CCC and others that had been rejected. And so we can do the record linking and then do the information. Okay, so all of this is really built on, so the linking part, well, so here's an example. This guy was from the file they gave us. We just put him on the tree, and I'll talk about that in a second. It's a genealogy platform where you can put genealogical information, and then we just attach sources. And so you get a whole bunch of sources for that person. Okay, so let me now show you specifically record linking and how I think it is going to help solve a whole bunch of machine learning problems. I mean, here's the best way I could phrase what our lab is going to be able to do is humans do family history for fun. And they do it very carefully, and they spend a lot of time doing it, and they sometimes even know the person, and they might have information that nobody else has access to, and so they tend to get it right about 95% of the time. And so if we trust the decisions they make, we could potentially have whole bunches of training data. So this is what we're envisioning trying to create, is each person would have a profile, they'd have a birth date and a death date, and then we'd have each of their census records, and then we'd know who each of the people that they're related to. And then each of these would have their own flat file, kind of like this. And this is an interesting case. So this is actually my grandpa, but actually my great-grandpa. He literally was not in the 1920 census. Like, we've looked for him every way possible, and he just wasn't there. And so this isn't just kind of an interesting case. And even in the best case scenario, you might not be able to match it. Okay, so here are the ways that others are linking records right now. And the nice thing is Rand put together some code. So if you're interested in linking records in general, you can go to this website and you can actually download the code for all three of these approaches. And then Martha Bailey has also put together some as well. She has a state of view file called AutoFind, and it will implement a lot of these strategies. I think right now there's this real goal to try to help just make it easier for other people to get involved in record linking. Now you might be thinking, I don't have to record link, I use modern data, but it turns out, like if you talk to Ben Hansen, there's a lot of administrative records you're going to get, and you sometimes want to combine those administrative records with others, and you sometimes think you can just do it using merge. And all it takes is like every little mistake. So actually, it wasn't this son, it was my other son. I got his birthday off by like 2 days, and they couldn't link it up to the insurance records. And so the insurance company then wouldn't pay for the ER visit. I mean, all I'm saying is like these like record linkages are a non-trivial thing. And so we can actually go back in time when it was even harder and use these methods. And then they're like, these methods can work really well on better, cleaner data. But so the fully automated approach by Ferry is what I would call a very smart person thinking through how they would do it by hand and then creating rules to follow to tell the machine how to do it. So there's no machine learning here. I would call this like human learning. So you embody in a very clever person that's done it a lot of times and then says, I think this is how much weight we should put on each of the features, and I think it should match exactly on this thing, and so you do that. Now, Abraminski takes a different approach, which is he says, I don't know anything about what we should link, let's just let the machine do all of it. Okay, and so it uses some statistical tricks to try to make that happen. And then the machine learning approach with Feigenbaum says, let's have a human actually go do the task. Okay, and then we're just going to give the machine the results of what the human decided, and then the machine will come up with the weights. So what we have here is we have a human choosing the weights. Here we have a machine choosing the weights without training data, and then here we have a machine choosing the weights with training data. Okay, so we're going to be using this third approach. The only difference is our training data is going to be like orders of magnitude bigger. Okay, and I'm going to skip these next couple slides to just show you kind of the ins and outs of these other approaches. And I can provide the slides if you want to see some of these other approaches. But I'm going to focus on this. So here's the machine learning approach. So this was James Feigenbaum's, and he was really kind of the first to use machine learning to try to link records. And the thing is, he had first name, last name, year of birth. He blocked on gender, and he blocked on the place you were born. Okay, so gender and place of birth had to match exactly, and then he said, okay, these are my other variables I'm going to use, and then he basically constructed measures from those. Okay, so like Gerald Winkler is a way of telling how similar two strings are, so he creates that for the first name and the last name, and then all these other features, and then he runs it through a logit regression, and gets predicted coefficients, and then he predicts matches, and then he has a cutoff score of what would constitute a match. Okay. There's another approach called support vector machine. This is the one used in Minnesota. And so again, all you're trying to do is figure out the weights to separate your categories into two groups. And I'll show you some code in just a second that we use, and it's really easy to implement, and it's very fast. And I'll show you how it is. Now, the thing you need to be super careful about is these would be like how to measure success. So one is your match rate. Is just how many of the records you're able to link together. Another is representativeness, which is, for example, if you only link people who stay in the same place over time, then you're gonna understate migration. And then you need to be careful about the false link rate, which is the share of matches that shouldn't have been made. And so Martha Bailey has a nice paper using past approaches. She compares it to her new training data and shows that one of the major problems with some of the past approaches was you get these really large false link rates. So just to highlight this paper right here, they might have thought that the match rate was 67%, but of those matches, more than half were incorrect. Now, in the context of their paper, it wasn't as important that they get the exact person to match, but you wouldn't want to use this method to try to link people together across records. Okay, so here's some stuff about training data. So this is from the Feigenbaum paper. So he had, I think I have the number, so he had 1,400 observations in his training data, and he just talks about how he created it using college students to decide. This other one had training data created by data entry operators, and then Martha Bailey has a large data training team. So let me just give you some numbers. Let's see if I have the numbers. I don't have the numbers, but the key thing is the training sets here are pretty small. So 1,400, I think 40,000. The key thing we're going to do is try to tap into a new source. Now the thing is, a lot of times they're using college students to link data, which is great. I mean, the ideal would actually be to hire a professional genealogist and let them use whatever information would help them make the right decision. And the cool thing is that there's a bunch of websites that allow people to do this. So we're going to be using data from Family Search. We're also working with Ancestry, but there's other companies like MyHeritage, WikiTree, Find a Grave, Find My Past. These all have kind of this desire to try to link together all of the world's population. Find My Past tends to do really well with UK records. MyHeritage does really well with marriage records, but each has their kind of strengths and weaknesses. Okay, so let me just tell you just a little bit about Family Search. That's this one in the upper right that we're going to be using. This is what it would look like if you set up an account. You'd have yourself, here's my wife, my kids, my parents, my grandparents, great-grandparents. And so what happens is I start to add my profile on there. And actually, Joe will check. I bet we're cousins. But let's just pretend Joe and I are like third cousins. Okay? And so what will happen, that means we have a great-grandparent in common, is I'm starting to add my stuff, and then I bump into someone who's already on the tree. And then I look and I was like, oh, Joe's the one that added all that stuff. Because if we have an ancestor in common, then we actually start to collaborate with each other. And so the nice thing about family search is it's a single tree that we're all part of. It's a wiki tree. And so then when Joe and I bump into each other, he might have photographs that I didn't know about. I might have some sources he didn't know about. But then everyone can see the information for that person, and we can start to add and fix each other. So I might make a mistake, and then Joe could come in and just be like, yeah, you totally messed that up, and he can just fix it. And so we get better data. So here is an example of a person profile. So here's a person he was married twice, he has kids, he has parents, he has siblings, and then for each of these, each person's gonna have a set of sources that are attached. And so you can see here's the 1900 census. This is interesting, he actually shows up in the 1900 census twice. Notice the middle initial is different. You can see him here, he's in the 1930 census. And so then I could link these records together and create a match pair. So this is how big our training set is. If you go from like 1900, 1910, you've got about 1.2 million women, 1.3 million men. So altogether it's about, and this is just for 1900, 1920. When you get up to 1900 through 1940, you get about 10 million matched pairs. So in contrast, LifeM has about 44,000, Vigalon has about 7,500. So what we're doing is it's really expensive to create training data, and we're able to grab a whole bunch for free because we trust the decisions people make in this this genealogy platform. Yeah.
So I mean, one of the issues of training set selection would be overfitting to that
Yes.
particular training set. So are you how are you sort of guarding against that? Are you doing like some cross-validation or something, or what?
Yes. Yeah.
Well, I was gonna say, a follow-up question would be, it's probably not random, the types of
It's
individuals.
not our training set is not
Correct.
random. That's right. Yeah. So we actually, so what we're going to be, so this is a non-random training set. We have another training set that's much smaller. It's about 100,000 matches, but it's a very different selection process that got it in there. It was coming from some other projects. So to be honest, if I wanted a training set with 10 million random observations, it'd be crazy expensive. And so a lot of what we're doing now is we will use the training data here to make predictions out of sample from a random sample. And then we hand check the predictions of a random sample of those. And that'll give us some idea about how well the predictions are doing outside of our training set.
So it's like a manual by hand.
Kind of a manual cross-validation.
Yeah.
So we can do a cross-validation within our training set. And I'm going to show you the metrics of those. We do really well within our training set. And I think it's partly because our training set is a lot of the easy stuff. So we do really well at finding the easy stuff. And we think that doing the easy stuff, you can get a match rate of like 50%. Then you have to think about ways to get the hard stuff. And so that's where we're trying to create other. So we've created a training set in Laredo, Texas. Laredo, Texas is 96% Mexican. And so they use a lot of the Hispanic naming conventions in terms of having two last names and other features that isn't well represented in this data. And so we're hoping, we also created a sample of interracial couples. And so we've been focusing on how to match interracial couples over time. But, yeah, I don't know so I don't have like a fantastic answer to your question.
It's more like a philosophical
It's more of a
question for you to
philosophical.
think about. Moving
Yes, we
forward.
could definitely create sample sizes like this of a random sample. And we kind of get those a little bit because when we make predictions outside our training set, then we go and check some of them and then we can feed them back into the training data. Okay, so we wanted to validate how good our matches were. So we compared them with the LifeM matches, which tend to be very good. And so, for example, here, we had about 1,000 where we overlapped, where they had a prediction and we had a prediction. And of those, we agreed 991 times, and then we disagreed 69 times. And then what we did is we just had people go and double check each of those 69. And so we found that the data we were using was right about 75% of the time. LifeM was right about 26% of the time. We were both right 4% of the time because actually the person shows up twice in the census. And then sometimes neither of us were right. And so then if you use the overlap there, you get that LifM is right about 95% of the time and the tree is right about 98% of the time. Okay, so that's one way to think about the quality of the training data. The other thing we did is we just drew a random sample, and then we just went and hand-linked from the training data, and we found that our human trainers agreed with the training data about 98% of the time. So we think the training data is pretty good. We did ask Google, we were curious, we had a Google engineer visit, and we said, Google, We could have a training set with like 40,000 that are perfect, or we could have a training set with 10 million that are not perfect. I don't know, what do you guys think Google said? Yeah, I said take the 10 million. You know, like the machine's gonna you're gonna feed it some stuff that's incorrect, but actually like feeding a machine lots of data is gonna help it figure out all the weird cases.
But this is part of the problem, right?
Yeah.
That nobody really knows, because a lot of these machine learning algorithms, they don't have like analytic convergence results.
Yeah.
It's like all kind of rule of thumb.
Yep. Yeah, so you're right. So then at the end of the day, you're going to want to validate your match scores in some way. And the way we're doing validating our match scores is by doing cross-validation within the training set and then doing the predictions outside. Now we have one extra advantage, which is we're working with Family Search. Family Search is a fantastic company. And what Family Search will give people are called record hints. So they'll say to a user on the tree, they'll say, we think this record is your ancestor. And so where do those record hints come from? Predictions of a model like this. And this platform has 7 million users. So you could actually potentially feed out your predicted matches to those users and see how the humans handle them. So I really think of this as an iterative process in which your training data gets better over time, your predictions get better over time, and the humans get a better product over time. But the thing about this is it has a built-in feedback loop, and I think that's probably the most important part of machine learning. And that's where I think the reason our lab does well is because we have 12 people doing machine learning and 30 people doing hand linking, and they're interacting with each other. I don't know, do you have is there a better way to approach this problem?
No, not at all. No, not at all.
I mean, it's hard.
Sorry,
It's hard.
sorry if my questions.
Yeah, no, I totally agree with you.
I think it's super cool, but I see this sort of trend in econ a little bit,
Yeah.
since machine learning is
Yeah.
like the shiny new
Yeah, for
thing,
sure.
that people don't always approach it with skepticism.
Sure, yeah, I would agree with you. And I think that's where Martha Bailey's paper was helpful. It kind of pointed out that maybe there was more false links than we would have thought, and that having some kind of truth would be helpful.
Yeah, and it's still, I think
Yeah,
it's
yeah.
super cool. I think it's super exciting, but I think that we also sort of, when we need to be thinking about things like like we're used to standard errors, right?
Yeah.
These algorithms also have sort of like
Built-in,
errors too.
we
and
have to incorporate that into our inference. Yeah, that's great. I think Ben Hansen had a great paper where he got some prison data and he kind of merged it using the traditional approach, and then he also got social security numbers and merged it using social security numbers. And I was surprised that even in like our good administrative data, this kind of false link stuff can happen. I think we just use merge all the time, and we just kind of take for granted that it's going to it's going to actually do what we think it's going to do. Okay, so here is the process. Let me just give you just a super simple example. So let's imagine the world only had 3 people, and there was only 3 time periods, and this is the way my data looked when I started. So the way to think about this is on the tree I have 2 people, we'll call them PID 1 and PID 2. And PID 1 has 2 of the years, PID 2 has 2 of the years. So my training set would actually have 2 matches that I could learn from. And then I have these other records that I don't know where they fit. So I know I have a person I haven't accounted for. And so among like E and F, I know one of them should fit here, and the other should be a totally new person. And then with G, I know that G should fit on that totally new person, and then H and I know one of them should fit here and the other one should fit with a totally new person. Okay. Now the nice thing about this is you can think about the math involved. So I have 7 rows, I have 3 people, and every time I find a match, I get rid of a row. So now I know right from the start I need to find 4 matches. And so every time I find a match, I know how close I'm getting to the total possible number of matches. And then notice that every time I find a match, so like if H matches with B, then it fits right there and that row disappears. And then you've got this new grid. And so the nice thing about the grid approach is then you know exactly which matches you need to check, and then in the end you end up with a final product that looks like this.
This is like a Sudoku puzzle.
It's like a Sudoku. But the nice thing is it helps you think carefully about how many matches you need to find, which are the possible matches, which ones you need to compare, how many comparisons you have to do, and you can start to think through like the computing time that it might take to do this problem. Okay. But then the nice thing about just doing this little bit of math is then now you know right away that you need to create 450,000 links. Okay, so every time, at the end of every day, I ask, like how many links did we get today? And, this is the number that we're aiming for over time. Okay, Or so that's kind of the
Can you talk a little bit maybe about kind of dimensionality issues, given kind of this process of, the rows and the number of possible combinations?
Yeah,
to think
so-
about? Is that,
Yeah, so this is where it gets complicated. I'm going to talk about blocking in just a second. Blocking is just the things that have to exactly match, and it's like the hardest decision you have to make. But it influences everything about your ability to find. So if you block very tightly, which means your block sizes are going to be very small, then your recall goes down because you're going to miss people that are outside the block. Whereas if you just go super loose, like you're going to say, well, I just have to have the first initial has to be the same, the last initial has to be the same birth date, same birth year, your blocks can get really big, and your comparisons can go way up. So I'll show you some of the trade-offs there. Now, we're going to make a trade-off that others haven't made, but it actually helps solve the problem a ton, which is I told you before, some of the measures of success is your match rate, your false link rate, and representativeness. We're going to take representativeness and just set it aside. We're going to say, we're going to start and not even try to get representativeness. Okay, this gives us a huge advantage, because one thing, and I'll show you what I mean by this in a second, is if you block on the town you live in, you can actually shrink your block sizes a ton. You can get a ton of matches. Now you cannot say anything about internal migration, because now you have a totally unrepresentative sample. But then you could try another one. You could say, I'm going to look at people who have a spouse, or are living with their parents, or living with a sibling. Turns out every time you have an extra family member, the ability to link dramatically increases. Because you're basically, whatever number of dimensions you have for the person, you get to multiply that by the number of dimensions of the other person. Now there's a bit of correlation, but it's still, so let me show you kind of those steps. So we have to first choose how to pre-process the data. So one thing we're going to do is we're going to fix nicknames, abbreviations. So there's about 1,700 nicknames and another 150,000 misspelled names. Actually, with last names, it's even worse. There's 10 million unique last names in the data, and we think only 500,000 of them are correctly spelled. So if you can kind of fix some of the misspellings, that can help you a lot. Then you identify the blocking variables that are stable over time, and then you have to use a machine learning classifier. Let me just show you these 3 steps. So here are the most common nicknames and abbreviations in the data, and then this is the Jera-Winkler score. So the Jera-Winkler score is the normal string distance. We normally, sometimes we'd have a cutoff that says the Jera-Winkler has to be, greater than 0.8. Well, notice that, if you don't fix some of these common abbreviations, you're going to just miss them right from the start. I don't know if it makes the top list, but Mary and Polly is an interesting case, where Polly's a nickname for Mary, and those aren't even close to each other. So if you go and fix the nicknames, you can actually clean up your data quite a bit.
Where did those come from?
From the training data. So what I can do is I can actually take every time I see William in one record, and I can say, how is the name spelled in other records? And so that allows me to create a crosswalk between these two. It gets even cooler than that, is that now I've got, basically, I've got a connection between WM and William. So I know that there's some connection between those names. And actually I can quantify the strength of that connection by the number of times I observe those pairs occur. You can actually then create a name network where you actually spatially locate all the names. And so then you can start to determine how similar two names are. So that could be helpful in terms of thinking about names that are closer to each other than others. Okay, now also using the training data, we can see which characteristics are stable over time. So for example, race ethnicity is pretty stable over time. Now to be clear here, my training data doesn't have a lot of African Americans, and African Americans do have a bit of kind of their race can change over time, what you would call passing. Okay. But other things like sex tends to be pretty stable, last name initial, last name Jera-Winkler, birthplace, birth year, last name Sandex. So what this is saying is these might be things you might want to block on because they tend to be very stable. Whereas if you look at something like father's birthplace or mother's birthplace, these tend to be very unstable. I was asked earlier why these are so unstable, and I don't know. I don't know how many of you know where your mom or dad was born, but what this means is when you ask me one year where my dad was born, I might say one thing, and then if you ask me at another time, I might say a different thing, and it just means that not everyone's quite certain about that thing. But this is also super interesting. City of residence. This means 73% of people are living in the same town from one census to the next. Okay, so if we block on this, this can give us a lot of leverage. Now we're still going to miss everyone that moved, but this could be a really powerful way to block. And then what this shows you is just if you combine multiple things, so this would be a blocking strategy, then like if you blocked on all of these, then you're going to be consistent about 85% of the time, and your average block size is going to be about 16. And that's doable. What this means is you're never going to have a match rate bigger than this, okay? Because there's 15% of the true matches that just aren't in your comparison set. That's going to be kind of the trade-off you're going to face as you think about different ones.
So I'm trying to think about the sort of, speaking of trade-offs,
Yeah, sure.
between say like, because a lot of the unsupervised algorithms basically reduce the dimensionality in the first place, like
Yep.
support vector machines,
Yep.
principal components,
Yep.
etc.
Yep.
So obviously you don't get the sort of validation with
Yep.
supervised,
Yep.
but I wonder if there's any sort of trade-offs that you can talk about between sort of the dimensionality versus the sort of blocking that you have to do.
Well, so let's think about. I'm not sure if I know the best way to answer your question, but here's one way you could think about it. You could take the support vector machine approach. You could take Random Bramsky's approach. You could take Joe Ferry's approach, and you could actually use those to predict matches. And you could then feed them into your comparison set. So the nice thing there is if those approaches are picking up matches that your blocking strategy doesn't get, then it gives them kind of a second chance to kind of get into the pool.
It would also be kind of interesting to see if the sort of unsupervised, I guess you could think of them as like an unsupervised block,
Yeah.
like if they're correlated with your.
Oh yeah, for sure. That'd be great. I mean, so when we have Random Bramsky's code, which is an unsupervised form of machine learning, it takes a long time to run, and we definitely want to compare what we get to what he gets, and then we'll do the same thing we did with LifeM, where we take the ones where we disagree and then have humans check to see how it ends up. Okay. But yeah, so blocking is an important thing you have to do. You have to block in some way. You can't just take all 200 million people and match them up against 200 million. Okay. So we use this iterative approach where we start by matching things that are easy to match, and the nice thing is sometimes one person's easy to match, and once you match that one person, then it's easy to match the other household members. Okay. So maybe someone has a unique first name, so you match the unique first name, but then you kind of get the other people there. And then the other thing that's helpful as, like if you take a last name like Savia, once I've matched 50% of the Savias, then the Savias that are left over might become easier to match. So maybe there's 2 Joe Savias to start with, but once I've taken half the Savias away, then there's only 1 Joe Savia left. And so we just call that the leftover problem. Okay, so let me just show you machine learning part. So the supervised models we use are random forest, gradient boosting, and XG boosting. And I'm going to show you some statistics on how well they work in this context, and I'm just going to give you some code. And if you want, you can Google the code. It's really easy to implement in Python. Most of the hard work is just getting your data to have the structure that XGBoost is expecting. So if you were to look, and I'd be willing to share our code with you if you wanted, but if you looked at our code, you're going to have 100 lines of code getting the data ready, and then basically 5 lines of code actually executing the machine learning part. And the nice thing is that getting the data ready, that's stuff you already know how to do. I mean, and you can do it in Stata. So that's, basically I could show you what the file needs to look like, and you know how to do that part. I'm going to show you machine learning isn't quite as scary as it's made out to be. Okay. So this is a decision tree. So underlying all the methods I'm going to use is just the basic idea of a decision tree, where maybe you're trying to predict whether it's going to rain tomorrow. And so you have some features, maybe temperature, wind, or air pressure. And so all the decision tree is going to do is try to think of cutoff rules that are going to put people into the right bins. Now, random forest is just a way of doing a whole bunch of decision trees and then aggregating the information across them. XGBoost is a variation of random forest that just learns from its mistakes as it goes. Okay, so here are the 4 that we looked at. XGBoost did the best, and random forest, and gradient boosting. So these were all 3 that are based on decision trees. Then logistic regression is the one that probably economists would be the most used to using, and then neural nets is another thing that's been used in the past. Now the ways we thought about it, precision is just of the matches we said were true, what fraction were actually true. Recall is of the matches we could have found, how many did we find? And then we actually like to include processing time because it's a helpful trade-off for thinking about how to balance these different things. And so actually the nice thing here, usually you think there'd be trade-offs, but in fact, we found XGBoost to do better on almost every category. And if you look, it's actually crazy fast. Okay. Now, if you were to ask a computer scientist, they'd probably say use random forest, because random forest tends to be the best across a wide variety of applications. But in our case, the XGBoost does quite a bit better, and it's quite a bit faster. And so if you wanted to do XGBoost, this is what your code would look like. So this is just the part of the code that involves the machine learning part. And so as long as you got your text file to have the right format, you basically just read in your data, you assign some parameters to the machine learning model, you would tell it how many rounds to do, and then this is just telling it, okay, I'm going to train this using XGBoost, these are my parameters, this is my training data, this is the number of rounds I want you to do, and then you just make your predictions. And then after that step, you would have a set of predicted matches. So this part of the code isn't too bad. Okay, so from what we've been able to do, we created this many matches between the different census records. So we've created about 43 million links between 1910 and 1920, out of the 75 million possible. So this gives us a match rate of about 56%. And our sense is that we'll probably hit 70% by the end of the quarter, and then our hope is to get up to about 90% by the end of the year. We think that there's people that are just going to be unmatchable, and we're not sure. At that point, we'll just do some training.
Are you doing this on like AWS, or like you have your own computing clusters? Or?
Yeah, so we're not using AWS. That'd be awesome to use. We have just a supercomputer BYU that we use, but we actually a lot of this stuff you can just run on just a single machine if you let it run over the weekend. So, I mean, here's the thing with AWS is it's kind of expensive, and I get lots of money for students. I don't get a lot of money for computing time, and so I will sometimes replace. It would have been, to be honest, it'd be a lot cheaper. It'd be a lot cheaper to use AWS, but I have a lot of students and I have money for students, and so you can sometimes get the students to run code on multiple computers and get them to think about this way to parse up the problem, and so you can often solve a computing problem with a labor solution. Okay, and then this is just showing you the match rate for different groups. So I think what surprised people the most is that if you look at, so male head of household, we have a match rate of about 55%. Now most papers in the past, actually this is probably an even better comparison. Here's sons and daughters. Most approaches in the past haven't even tried to link women. And so actually we're having match rates for women that are pretty good. Okay, they're always a little bit less, but they're not that bad. And then related to your comment, these are the boarders and the servants, and they're really hard to match. But even them, we're able to match some of the time. And again, this creates huge data sets that allow you to study lots of employees. Okay, so I don't know, any questions about the method? I'm just going to show you some things you can do with it. And then if anyone wants to reach out afterwards about the things you would want to do with it. And then in terms of our goal, in terms of public dissemination, our hope, the challenging thing is we're working with Family Search, we're working with Ancestry. These are fantastic companies to work with. It's just this is a complicated intellectual property environment, and so we keep our Family Search stuff separate from our Ancestry stuff. But at the end of the day, we also have our own training data. At the end of the day, we're trying to use our own training data to create a product that we could share through IPLMs or through MDR. And so, I think you'll see this data become more useful and user-friendly in the future. So any questions before I show you a couple applications? Okay, so here we go. So let me just show you, these are 3 things that we're doing with the data. And one is a replication of something Raj Chetty did this summer at NBR. One's having to deal with does alcohol during childhood affect long-run outcomes, health outcomes, and then the last one's about prejudice, and particularly prejudice that is unexpected. So if you think about, it was motivated by a paper related to 9/11. When 9/11 hit, it created a lot of extra anti-error bias in the United States, had a lot of consequences for people's lives. And so what we're going to try to do is study that phenomenon. But it's something that's less emotional for us today. We're going to go look at when we hated Germans back in 1918. Okay, so these are a couple things that we can do with the data. Okay, so first of all, we're just curious about the intergenerational correlation of lifespan. There's a lot of research about the intergenerational correlation of income, occupation, and other things, but lifespan is an interesting thing that you might be able to pass on to your children. So we have a sample of about 9 million people. It's primarily white, though there's about 200,000 blacks in our sample, and we're working hard to make that a bigger sample. And we just want to know what is causing the longevity gap between blacks and whites. And will the longevity gap between blacks and whites disappear over time? So we're going to approach this the same way Chetty did with income, using the Social Security data. And so I'm actually going to create a graph that mimics the Chetty analysis. And the nice thing about the Chetty analysis is it allows you to think about the steady state difference. And we can think about whether the steady state difference is bigger or smaller for lifespan than it is for income. So I'm going to have you just make a guess really quick. So what is your prediction? Okay, so think about your prediction. I'm going to show it to you. Okay, is the intergenerational correlation larger for income or for lifespan? Okay, so all I'm going to do is I'm going to show you Chetty's graph, and so you can think about both the degree to which parents can pass this thing on to their children, and then I'm going to show you what's likely to be the steady state gap between blacks and whites going forward. Okay, so here's the Chetty graph. So what he does is he rank orders all the parents in the sample based on their income, and then for each of the percentile cells, he comes up and he finds the average child rank, and then so this is this rank correlation. And then he does it separately for whites and blacks. And then he draws this 45-degree line. And then the intersection point will give you the steady state. Okay. And so what you can see is that what was really interesting about what he found is that actually the relative mobility was nearly identical. But the absolute mobility was pretty big. And this leads to a big steady state gap. So let me show you the same graph for lifespans. It's going to have the same features. It's going to have two slopes. It's going to have the two intercepts, and it's going to have the steady state. So remember, if you think that lifespan has a higher intergenerational correlation, then these lines are going to get steeper. If you think it's lower, they're going to get less steep. Okay. So let me show you the two graphs. Okay. So do you see what happens to the slope? Okay, much less steep. Okay, in terms of the relative mobility. The absolute gap is also a bit smaller. And then, so as a result, the steady state gap is about 5 percentiles. Okay, so in contrast, when you look at income, it's about 15 percentiles, whereas with lifespan, it's about 5 percentiles. Okay. And so this helps us because then we can start to think about what is it that parents can buy for their children, what can they give to their children. And so even though you can find ways to increase your child's standard of living, this would indicate that actually the world's a lot more fair in terms of lifespan. Okay, and so you can start to think about why that is. And actually in a separate paper with Amitabh Chandra and others, we were actually looking at the raw gap in lifespan between blacks and whites. And then we include state fixed effects, and then county fixed effects, and city fixed effects. And the city fixed effects make a lot of the gap go away, which then helps you start to point to some of the factors that might explain why there's a gap in the first place. Okay, so here's another possible use of the data. So the other thing you could do is you could go back in time and just look for interesting policies. So I think with Catalina, we were talking about child enforcement or immigration enforcement. So I'm like, were there any policies before 1950 regarding, or with you, I asked if there was any trade shocks that. So you can think about policies that might have affected at different times. And so Casey and I were interested in alcohol exposure during childhood. And we know a lot about alcohol exposure while you're in utero. We don't know a lot about alcohol exposure while you're a child. Now there's an interesting thing right now in India, where India's per capita consumption of alcohol is very high. And once you account for the fact that in India, women don't drink alcohol, then if you do like the per male capital, it's like worse than Russia. And so you have these rickshaw drivers who will spend half their income on alcohol. And the women in the community start to push for prohibition. Okay, not because they're like upset at alcohol, they just want more of the income coming back home. Okay? So what we're curious about is the United States also went through an interesting policy variation. So this is prior to national level prohibition. So we're not even touching national level prohibition. Prior to national level prohibition, counties began to experiment with prohibitions. You have dry counties and wet counties. You'd also have counties that were next to a dry county or next to a wet county. And so this is just a number of states that had prohibition laws. And then what's even more interesting is that within a state, so like here's Alabama, you can see that even within a state, the number of counties that are dry changes over time. And you see that across states, that within state variation is also pretty high. So the thought experiment here is, I know where you were born, so I know your county of birth. I also know where you were living every 10 years. So if you want, you can think about birth county versus the place where you're living. So I can observe you changing your location over time. I can also observe siblings. So I can have, you might have been exposed to prohibition because your family moved. So you've got this nice mover stayer within family variation. So we're just going to exploit both the temporal variation, cross-sectional variation, and within family variation. Now this is just to give you an idea of whether a matched sample is representative. So what I have here is this is the population. So there was 23 million people we could have matched. Now in this case, not only do we have to match you basically to a death date. So these are people living in the counties when they were a child during the policy variation time, and of those we were able to find death dates for about 5 million. Now the nice thing though is, aside from a couple factors, it's pretty representative. So first of all, I will always acknowledge, so most of our analysis we're just going to run just on whites, because this is a problem we're still trying to fix. But if you look at a lot of the other characteristics, it matches up pretty well with the population. Now the other thing we can do is we can also match up the mortality rate with the population, and so we can actually match the vital statistics pretty closely. Okay, so we think the X's are pretty similar, and we think the distribution of Y's is pretty similar. Now there's still other factors that we can't match up exactly, but this just makes us feel like once you get a match sample that's big enough, you might actually start to be able to replicate populations. Okay, and so now what I'm going to do is I'm just going to estimate a regression in which I look at the fraction of your childhood that you spent free from alcohol on your mortality later in life. So this graph is going to just basically show you the coefficients at each age. So right here, you can see that there's not a lot of difference in this range. Okay, and so then these health effects of being exposed, or basically being exposed to prohibition, have these positive effects of about 1 percentage point, in terms of you're about 1 percentage point more likely to survive to different ages. So again, these would not be effects that we could have detected just by using mortality right away. This actually really involves us being able to trace out your whole life trajectory. You look like you have a question, but go ahead.
Could you look at this based on the parents' education level? Or
we could, yeah. Well, so here's the one challenge with parents' education level. We're linking people, these people were all alive in the 1910 census.
Right, so it's all pretty low.
And so I don't see education until 1940. So I could do it.
You have occupation?
I could do it by occupation. We could do it by occupation score. We could do it by occupation score. So you're thinking that there's like some people that can handle their liquor better than others, or they have more income
There's a different
disposable.
distribution of usage.
That's a great. I think actually doing it by occupation would be a really good. That's a great idea. Because I mean, when I think about the rickshaw drivers, it's not just that it's the alcohol; it's that it's consuming so much of their income. Whereas if you were more affluent, if you had a better occupation, then you could handle it. Okay. Let me show you one last application. This one, we have a really cool identification strategy. I don't have results, but so what I'm curious about here is audit studies tell us a lot about the partial equilibrium effect of prejudice, which means that we know that when people apply for a job, their characteristics might influence whether or not they get the job. Now, we don't know is how people respond to prejudice over time. And that's just a partial equilibrium effect. The general equilibrium effect might involve that they just stop sending out applications, or they don't even try to go to college in the first place, and so it could affect every decision up until that point. So we need an exogenous source of prejudice, and then follow the long-run effects of prejudice by those who are impacted by it. So today, it's about anti-Muslim or anti-Arab prejudice, which is hard to study. In the 1910s, it was anti-German prejudice brought about by World War I. So how do we get the cross-sectional variation? Okay. Well, here's just an interesting fact. In 1910, there was about 2.5 million Germans. These were German-born Americans. And in 1920, that number had dropped by almost 1 million. So 32% of the German-born Americans just disappeared. We've been able to hand-link a lot of these. And what they did is they just said they were born in a different place. They'd say Poland, Bavaria. The funniest ones is like Bavaria and Bohemia, which are parts of Germany. Apparently there would be like nobody would know that, so they think it was like somewhere else in Europe. And you can see Austria also dropped a lot. So these are big changes in that. Okay. So we know that something big happened to Germans and Austrians. Oh, I don't know what happened in Ireland. Were you going to ask about Ireland? No. But we're going to find out. Now, one thing, so then we start looking for high frequency measures we can look at. Now, the problem with the census, we only see you every 10 years. Well, the nice thing is that patent applications are happening on a continuous basis. So what we did is we looked at every patent application in the United States, and then we looked at those who have a German last name. And so you can see right here, there's a big dip during World War I, and then another big dip during World War II. I think the thing that surprises us is how quickly it bounced back up. Okay. But you do see that immediate dip right there. Now this is again just temporal variation. So what we want is cross-sectional variation, and this is where we got the cross-sectional variation from. So there's a book that lists the names of every single US soldier that died in the war and where they were from. Okay. So it's about, I think it was about 80,000 US soldiers. And we were able to link every single person back to a town. And then we focus on towns, so you can see like, just on this list, you can see some of the bigger towns like Pittsburgh and Philadelphia. We focus on towns that were small enough such that 100% of them weren't treated. So once you get down below a population of about 100,000, then you actually will have some variation. And so then we have treated towns and control towns. And our identification strategy actually comes from a movie with James Dean called East of Eden. And there's, if you watch this movie again, it's a great movie, but there's a scene in which the town, a soldier from the town dies in the war, World War I, and the town gangs up on the German family. And James Dean comes to their rescue and says, I don't get it. Yesterday they were our friends, and today we want to kill them. And that's what we think happened here. We think that a lot of prejudice actually is driven by an emotional reaction to something. So 9/11 would be a good example. And so World War I created something similar. And so we actually think this is going to give us cross-sectional variation. So by linking each of these people back to a town, we now have treatment towns and we have control towns. And so then, now getting the, now let me be clear, I made this sound like an easy problem, but a lot of these towns are misspelled or OCR'd incorrectly. And a lot of these towns actually aren't like real towns, or they're not like census towns. So the census has about 30,000 towns, but a bunch of these aren't real towns. And the other thing is not all these guys died. So, so they got in the book. Sometimes, you know, they were wounded, which, so what we were able to do is we basically grabbed data from every military cemetery in US and France this time period. We also got all the World War I draft cards and we had census records. And then we basically treat this as a sparse data problem where all we have is a last name, a first name, and a place. And we can approximate their birth year. We think it's about 1896, and we know they died in 1918 because all the US deaths happened in a very narrow window. Now the nice thing about solving this problem, so we've solved this problem, but it has some cool applications for school yearbooks, homeless shelter records, political donations, patents, are all situations where you have a name and a place and a guess at the age. And so if you can actually link records that only have those three features, then you can do a lot of cool stuff. So one cool thing you can do with high school yearbooks, so we've been linking yearbooks to census records, you can actually recreate school boundary files. And so you can do stuff on people on either side of a school boundary. Well, homeless shelter records is more like a modern application, but this is when I was talking to someone that they said that we're not quite sure what to do with this data because we can't link people, but sparse data linking could potentially solve that. Okay, so here are all the US deaths. Again, US showed up very late in the game. The armistice happened in November. And so we got there late. Everyone died in a very narrow window. We do still have some variation. And now some of these deaths up here where they died of wounds, and so they didn't die right away, but we have the exact date that they will die. Okay, so this is the one thing that we can do right now, and then I'll show you what we're going to be able to do with this really soon. So this is just the use of German names. So Wilhelm is a very German name. Franz is a very German name. And so you can see actually, these are our, the red is the towns that had a death occur, the blue are the towns that didn't have a death occur. And so you can see that they were pretty similar to each other. And then right here, right in 1918, you see this bifurcation between the two. Okay. Now we're trying to get birth certificate data, because then we can get super high frequency data. And we could actually look at the date the first soldier died in your town and try to get it. But again, this is just kind of some suggested evidence that something changed.
Could you also code the deaths by like whether they have German names?
Yeah, so to do that, oh yeah, so that's a great idea. I need to do that. We were actually linking them to their census so we could actually see if they were German or not. You're right, we should definitely do this by German name. So because your idea is that
It's like maybe you don't care.
you don't
like,
care. So if it was a German that died, then
yeah.
kind of is even Steven, and we're not going to get upset. No, I think that'd be a great idea because that'd give us one extra
That
source
sounds
of
good.
information. Okay, and so just to give you an idea of the kind of things you can do with the data, so some of the outcomes are names, intergroup marriage by marriage date. So we have the marriage records. We can see if it became hard to marry off your daughter if she was German. The death dates of Germans. So there was a lot of reporting of kind of lynching behavior. We don't know actually if it affected death rates, but it might have. And then you can look at the crosstown variation in 1920 outcomes. You can look at whether people moved, changed their occupation, intergroup marriage, and whether they changed their name. And then in the 1940s, you can look at education, income, occupation, whether they live in an ethnic enclave or intergroup marriage for all of their children. Okay. So what this allows us to do is you have a shock that creates prejudice against a group, and then you can follow up the effects of that. And then when the 1950 census becomes available, we want to do this with the Japanese, which is another kind of group that faces this. Okay, so just to conclude, here's my pitch. I think if we bring together family history tools and machine learning tools, we could potentially link together all of the census records in the United States, and there's no reason to stop there. Every single college library in the country, every archive, every home is full of records that have potentially useful things. One thing to think about, companies keep employment records. When I was in Hawaii, the plantations had these crazy, amazing records where they have the wages of each worker over time. So you can imagine that we could potentially tap into records that we never thought useful for economic research. And so I think the real value is going to be by trying to partner academics with machine learning tools with people who want to learn more about their family, that the three working together will ultimately link together everyone. And the other cool thing about this is once we link together everyone, then we will know how connected we are. So I think, Catalina, we couldn't discover if we were related, but maybe we are. And so, but I think this is going to open up lots of interesting areas of research. And then I think we're going to be able to see how long people live, why they die, and see their entire life. I think I'll stop there. If there's any questions.
Thank you. Great.